much. I just want to apologize to everybody for my absence. I was all set to go, but I had an unforeseeable family event that prevents me from being there. And I just would like to thank Mike and Chris and the organizers for allowing me to proceed. Anyway, I wish I were there. I've been a big fan of this mission for a long time. I was echoing Priya's comment yesterday. I was at the same conference at Carnegie. I have no idea what the year was when this thing, I think this was before it was called Axis. And it's a great mission. And so I'm going to talk about stuff that is not, that's a little bit different from what I've done in the past, although this is stuff that I did with a postdoc. And I'm going to reference stuff that other people have done long before I got started. And that is to try to look at elliptical galaxies and understand whether they're scaled down analogs of clusters. And that's the overarching question that I'll try to address here. And the answer is probably, but it's unclear. And I think Axis is going to have a huge statement to make about this in the coming years. So to start off, I'll just show one of the more spectacular cluster examples of feedback from black holes. This is the Phoenix cluster, made famous by Mike McDonald and his students. On the left-hand side, you can see the HST continuum showing all this blue light. That's star formation. It's forming stars at several hundred solar masses per year. And in the center, you can see the oxygen-2 emission being pulled up. The X-rays aren't shown here, but it has giant cavities, which are shown as ovals there. And you can see all of this material, cool material drawn up, and star formation occurring in this cool material. And then on the right-hand side, you see a Chandra image. Let me see if I can. I'm having a bit of a technical issue here. Okay, much better. And on the right-hand side, you see a Chandra image from 0.5 to 7 keV, and you see all these cool filaments being pulled up. And examples of these are widespread in clusters of galaxies. And the question is, do we see these in groups and ellipticals? And the answer is yes. Here we see a little gallery of galaxies, NGC 1399, 4472, 4636, and NGC 5044, which is a small group. And you can see the X-ray atmospheres on the left are they're all beaten up, and this is due to jet activity from the nucleus. And on the right-hand side, one of the earliest ones found with Chandra's M84. And you can see the blue light there is the X-ray emission from the atmosphere, and in red you see the jets. And NGC 5044 below shows not only all this cavitation due to the jets, but also extended emission lines in the elliptical galaxy. Note that these have very high density cores and very short cooling times. So the cooling times down in the center. The scales here are much smaller than what I showed before. This is structure on scales of a few kiloparsecs, whereas in clusters you see them on tens of kiloparsecs, in some cases hundreds of kiloparsecs. So from this perspective, there are indications that they are scaled down analogs. Now, what are some of the questions that we're trying to answer over the last many years? Is how is feedback sustained? Is it hot accretion? Is it molecular gas accretion? The answer may be some combination of both, but we don't know. How do jets and bubbles heat? This is a question that's really at the forefront right now, and I'll show some spectra from CRISM at the very end that addresses this, but it's unclear. Is it bubble entropy? Is it a turbulent cascade? Is it cosmic rays that are leaking out from the bubbles? Is it just mixing of the hot and cold material in the atmosphere? Is it some combination? And is a single mechanism from doing this from ellipticals to clusters? This is an important question if feedback is ubiquitous, and I'll show some evidence that it is. at least from jets over time. It would be comforting to think a single mechanism is doing this, but it's not necessarily the way nature works. How do atmospheres become thermally unstable and cool? That's been a big question for the last 10 to 15 years, and we still don't understand it entirely. It may be due to local effects, but it could also be lifting. The bubbles themselves may actually enhance thermally unstable cooling. This is all being worked out both theoretically and experimentally. And of course, at what halo mass and when are hydrostatic X-ray atmospheres established? This is something that we don't know, and the huge throughput of AXIS is going to play a big role in answering that question. So what excites me most, I think, and AXIS is going to, to do much of the science that I and others have been doing on rich clusters, and it's going to do it even better than we have. But I think the big thing it's going to do is it's going to allow us to push to lower masses. And this is really important. So on the left-hand side, what I show is the ratio of stellar mass to halo mass. It's a famous plot that most of us, I'm sure, have seen. And you can see that as you go to lower halo mass, the efficiency of conversion of baryons into stars increases. And then as you go to very low masses, it suddenly drops. And as you go to higher masses, it drops. And these drops are thought to be due to feedback at the high end, due to AGN feedback, on the low mass end, largely due to winds from star formation and supernova explosions. There's a lot of some growing evidence that AGN play a role even in the low mass systems as well. And then on the right-hand side, what you see here is a plot of the luminosity, X-ray luminosity within 5 effective radii versus total mass. And you can see that there are many measurements at high masses where we can observe easily with Chandra and XMM. But as you go to lower masses, things start to peter out. And here's we're subject to lots of selection here because these targets are just pulled from the Chandra archive. So there's a strong selection bias. And I think going to these lower mass systems will be very important. And the questions that we can ask then are, at what mass do hydrostatic halos play a role? And they're very important for creating buoyancy, which allows the energy from jets to permeate the atmospheres, the outer parts of galaxies over very large volumes. And I'll show you some of the implications of that later. But this is the direction that I think is going to be really exciting, that AXIS is going to take us. Now, this is a plot that's been shown over many years. On the left-hand side, this shows the jet power from radio jets measured using X-ray cavity enthalpy, which is the PV work plus the internal energy of the X-ray bubbles. And there's a little example shown on the upper left. And on the right-hand side, that's the cooling luminosity, or the radiation that has to be compensated to prevent overcooling in the atmosphere and creating giant galaxies that are much bluer and forming stars at much higher rates than are observed. And what you can see here is this line going through the center at 4 PV is approximately equality between heating and cooling. And the remarkable thing about this plot is it shows that there is a rough balance between heating and cooling, with, of course, departures, as there must be to keep a feedback system going, from central galaxies and clusters all the way down to ellipticals. But as you get down into the ellipticals, you can see that things start getting pretty dodgy because the measurements are much tougher. We have many fewer photons. But there is an indication that that feedback is a continuous process down to low halo masses. But it's still an open question, and it's something that needs to be, I think, explored and will be explored in an exciting way when AXIS is launched. Another important question is how radio feedback scales with halo mass. The previous plot just showed cooling luminosity. Now we can look at it as a function of mass. And indeed, feedback it knows about the gas surrounding it, how fast it's cooling, which is a remarkable thing in itself, given that all of the action creating the energy is occurring within a few Schwarzschild radii, yet it knows about what's going on over an enormous volume. And this is also true in halo mass. And so what's shown here on the left-hand side is feedback power, calculated again using cavity enthalpy versus halo mass. And you can see this large trend over 3 orders of magnitude in mass, where we go from clusters down to groups and galaxy scales. But the data peter out pretty strongly once you get down into groups and galaxies. And again, here is again the place where Axis will populate this part of the diagram. And I think that will be very exciting. The factor of 10 throughput is going to play a huge role down there. And there are also technical issues, as I'll show in a couple of minutes, with making measurements in groups and galaxies. Photons, you're starved for photons, and it's very hard to simultaneously measure, for example, temperatures and metallicities in the atmospheres. And this is just a function of photon counts, and we need more, and Axis is going to deliver that. And what I just stated is succinctly shown here. In clusters where we have a wealth of photons over a very large volume, this is the Hydra A cluster shown here, which is I'm going to show some new results from this object a little bit later on. But what's shown here on the left-hand side is this enormous, on the left-hand side, you can see this is an X-ray image, an unsharp masked image, and you can see it's filled with X-ray cavities going out to a couple of hundred kiloparsecs. You can see the scale bar in the lower right on the right-hand side. But then what's shown is a metallicity map. And one of the things that we've learned in clusters is that these jets are dragging material, cooled metal-rich material, and dragging it outward. And this is something that we would like to see in ellipticals. And this is, I think, pillar 2 of the Axis science case. But in ellipticals, it's extremely hard because we don't have this marvelous wealth of photons that we can get in the Hydra A image. So to just give you an example of how things are, on the lower left, there's a plot of metallicity versus X-ray luminosity. And the only point I want to make here is look at the error bars on that. You can see just as soon as you get down to luminosities below 10 to the 41, the error bars become huge. And so it's impossible to do something like what we're doing in clusters in normal ellipticals. And then on the right-hand side, quite similarly, you can see the X-ray luminosity plotted against gas temperature. This is results from Kim and Fabiano. And you can see as you go to lower luminosities, the temperature errors become very large. Well, why is that worrisome? It's worrisome because we want to study these systems as a function of halo mass. And we need temperatures to do that. One temperature is fine for a rough estimate of the mass, but ideally you'd like to get several temperatures to measure a temperature profile when measuring hydrostatic masses. And in most cases in ellipticals, that's not possible because we just don't have enough photons. And with the spatial resolution and throughput of Axis, I think this is going to be a huge area for progress. So of course, when in feedback, half of the loop is cooling. We need a mechanism to get material down to the black hole so that the whole operation can respond promptly to maintain roughly to maintain equilibrium, so that we don't get huge mass dumps, which happen, cold mass dumps into the central systems, and in some cases to keep them essentially free of cold gas, at least measurable cold gas. And so we wanted to understand whether similar correlations that we've seen in clusters between molecular gas mass and, for example, central gas density, central cooling time, and so on. There are any number of parameters that we've looked at. And in clusters, which, the left-hand side here shows the molecular gas mass versus X-ray gas mass within 10 kiloparsecs, both for cluster sources and ellipticals and groups. And on the right-hand side, it shows the molecular gas mass versus just the gas density at 10 kiloparsecs. And what you can see in the clusters, if we were just to isolate the clusters alone, there's a very strong correlation between molecular gas and the gas density in the cores of clusters. That gas density also translates into short cooling times. And so we see a clear relationship between the molecular gas and cooling. And molecular gas masses observed at the centers of clusters are quite huge. Okay, you can see that they're well above 10 to the 9, and in many cases approaching 10 to the 11 solar masses. And it would be very hard to explain molecular gas masses of that magnitude by mergers, which is these are commonly attributed to mergers, but that would be very hard to explain the correlation, strong correlation between X-ray gas density, cooling time, and the levels of molecular gas. But that becomes dodgier when you get down to the ellipticals and S0s, SAs, and SBs. As you go down, you can see there's an enormous scatter. And in fact, you would not see a correlation if you were to just break it up. Between the clusters, you see a correlation. You would be struggling to find a correlation for the ES0s and SABs. But they do lie along the extrapolation of the cluster line. So one of the other issues that, and certainly a theme of this conference, has been multi-wavelength observations. And of course, to study feedback, we must study it from the coldest gas to the hottest gas. A lot of the uncertainty in the measurements here are associated with ALMA observations, just getting, and single dish measurements of molecular gas. And so to explore this question of whether feedback pushes down, to the lowest mass galaxies, and then, to what are the lowest mass galaxies, what are the lowest mass halos that support a hydrostatic atmosphere, we need observations using, ALMA and other telescopes in a coordinated way to get these errors down. And so you can see that the errors blow up here, both on the left-hand side here, molecular gas, and on the right-hand side when you get down to the low mass systems. But also some of this scatter is just in the X-ray measurements. And I think larger samples with much better measurements made with AXIS will be very exciting indeed. And this is a bit of a summary that again points toward this continuity from clusters down to individual elliptical galaxies. This is work by Lakchara 18, and similar work was done by Babik as well. And what you can see here is density, entropy, gas entropy, and cooling time presented in 3 panels versus radius in kiloparsecs. And these are all groups and galaxies. And in color-coded, in red, it's free of cool gas. In green, these are systems that just have nuclear cool gas. And cool gas can either be nebular emission or molecular gas. And then in blue, they're extended cool gas in the same sense that I showed earlier that we see in clusters. And what this plot shows is that you, on average, tend to see in normal ellipticals extended cool gas where the atmospheres have higher gas densities, have lower entropies, and have shorter cooling times. And this is also quite similar for galaxy clusters. But you can see there's a lot of binning going on in this representation. And if you do look at the formal errors, they're sort of 3.5, 4 sigma. That's generally not good enough. And I think this is a problem that AXIS will nail in its first 5 years. And then finally, on the thermodynamic properties, this is, I think, kind of a remarkable plot. This shows the gas entropy versus radius in units of R2500. It's a combination of 40 ellipticals and 110 clusters. And what it shows is this break in it's a double power law. It can be fit by a double power law, where to the upper right, you can see this entropy scaling R to the 1.1. This is a well-known scaling, the expected scaling of gas entropy, assuming just gravity alone. That is, cooling plays very little role there. For long cooling times in the outer parts of clusters, you expect, a K to the R to the 1.1 profile. This is something that Mark Voigt and others have shown years ago as a general quality of cluster atmospheres. But then as you get into the inner regions where the galaxy is, there's a break in it, and the entropy scales as R to the 2/3. And it's a very interesting region there because, when K is proportional to R to the 2/3, and when you assume an isothermal mass distribution, which is generally you can model the stellar mass plus the gas mass in the inner regions as an isothermal. At that point in there, the ratio of the cooling time to free fall time becomes a constant. And for many investigators, that ratio is really key to when thermally unstable cooling and fueling of the atmosphere can occur unhindered. And so in that region, whether or not that thermodynamic parameter is really driving things is unclear, but it certainly almost certainly has something to do with it. That's where the cooling gets unstable. And you can, and fueling can be enabled in these systems. And it looks like that this carries over 5 decades of jet power. And the remarkable thing is it's steady. We didn't pull the very powerful sources. They're all in there. And despite, being assaulted with this enormous power from the jets, these relationships hold. And it's just another way of stating that, and it's been something that's been very hard to capture in simulations. Feedback from jets is extraordinarily gentle, despite, systems that have powers upwards of 10 to the 61 ergs. What's at stake here? Well, this is a plot from Heckman and Best, which shows it's a census, a cosmic inventory of galactic feedback. And what they've done is taken the scaling relations between radio power and enthalpy that were developed by our group many years ago, and applied that to the Sloan Digital Survey, looking at an enormous range of mass and volume in elliptical galaxies. Well, essentially all galaxies down to a certain mass. And they did this as a function of look-back time. And the surprising result and very interesting result that they found is that the energy budget across all galaxies over time is dominated by jets. It's actually not dominated by quasars. That's not true of the momentum budget, but it is true of the energy budget. And so what I've done here is added some comment to their figure. In green is, I think, an optimistic estimate of where we've been able to measure enthalpies, gas enthalpies, in clusters of galaxies that they've used to calibrate this diagram, and it's actually closer to 0.5. And so the question is, does this relationship stretch out as far as Best and Heckman argue that it does? Jets do seem to peak at about a redshift of 1, but they still dominate. The halos are the masses of the halos, of course, are growing as you go to lower redshift. And one question, of course, that comes to play here is, when are X-ray atmospheres, when do they become in place? At what redshift? And when do they become stable? Because the atmosphere is an absolutely essential element in taking jet energy converting it to enthalpy and impacting its surrounding areas. So that's another open question that I think Axis will be able to address. And finally, I'll just finish up with a tantalizing new result from CRISM. I think the 2030s will be exciting. If we're all lucky, we'll have Axis, Athena, and Lynx in the 2030s. Hopefully, I'll still be around to use them. But I just wanted to give you a hint of something that CRISM is doing that also is very important for the questions that I just mentioned in elliptical galaxies. And if, Athena, when Athena flies and hopefully Lynx fly, we'll be able to do this in elliptical galaxies too. And that is, we'll be able to measure gas motions in clusters. So one of the targets that we got in the AO1 is Hydra A, which I've already shown here. There's a bright central galaxy at the center of the cluster. You can see it's got an enormous X-ray atmosphere, and it has these huge X-ray, huge radio bubbles that fill the atmosphere. And we got a pointing roughly about the size of that square in the center, and I'll show you more precisely here on the left. But here's the image that I just showed with the CRISM footprint on the left-hand side, and then a blow up of the CRISM footprint. On the right-hand side, you see the lovely CRISM image, not so photogenic, but just beautiful photons coming from there. And I show you a blow up of the helium alpha iron 25 line, showing here the main line and the X, Y, and Z lines on the left-hand side. And we measured the velocity dispersion, and it's 164 kilometers a second, which is comparable to what we saw in Perseus. But the total power in this system is about 10 times larger. In the footprint, the jet energy is about 10 to the 60 ergs. The kinetic energy associated with sigma, which is the key, is about 10 to the 60 ergs. It's about half of the energy in the footprint, but it's a much smaller fraction of the total power that's emerging from the jets over the last 10 to the 8th years. And that the kinetic energy represents about 2.5% of the energy radiated away. Turbulent heating has kind of been one of the leading ideas, leading models for how enthalpy is converted into heat, thermal energy. The question is this a viable mechanism? I would say that the answer, the jury's out on this. We've been finding generally very small velocity dispersions. There are some instances where there surely isn't enough currently enough energy in turbulence to counteract cooling. In a couple of cases, in this one, the jury's out. I would say it's close, but it's unclear whether you can get the energy throughout the volume fast enough to offset cooling. And so I think this is a really exciting moment because this is a very important question, and I think CRISM will answer this with clusters. It won't do the job with ellipticals, but that may come in the next decade. Some of the key unknowns here are the turbulent dissipation timescale. We don't know what that is. We don't know what the proper injection scale is, and we can't measure it with this coarse spatial resolution. We also don't know how much of sigma is taken up in bulk motions, which may not thermalize so quickly. So I think this is an exciting result. We're seeing low velocity dispersions. Whether turbulence can do the job, I think, is a question that we should be able to answer in the next couple of years. So that's my presentation. I'll just summarize by saying multi-wavelength observations plus axis will really, I think this will be the key to determining whether it's a continuous run of feedback and how important feedback is across cosmic time for maintaining and shaping galaxies. And we also should learn what the lowest mass halos are that can sustain an atmosphere. But the current statistics, temperatures, metallicities, densities, they're just poor because of the low effective area below 1 keV. Is a single heating mechanism at work? I don't know. Right now, I would say probably not, but the jury's out. And so I'm just going to leave it with that and take questions. Thank you very much for having me.
Ryan, can you hear us? Oops.
I can.
Okay, great. So maybe time for just a couple of questions. I will ask one while people are kind of getting set up. So I don't know if you saw that CRISM press release on PDS 456 and just the amount of it was like 30 to 300 solar masses in a year or something of feedback through these ultra fast outflows. Do you think that is a viable sort of mechanism in terms of competing with jets for, extreme feedback?
It's always hard, with absorption, outflows measured by absorption. It's hard to know what volume they're affecting and how much, total mass is involved. The main thing that jets can do is they operate on vastly larger scales than the high speed outflows in the center. So the outflows in the center are working at scales of about a kiloparsec. The jets are feeding back and operating on scales of tens of kiloparsecs. And so they can affect the galaxy in much larger volumes. That's the way I would characterize that.
Hi, Brian. It's the other Mike. On your last slide, you had a list of sort of the unknowns in how the energy from the bubbles is being dissipated. Is there a lot of these are velocity measurements that we need? Is there something that Axis could measure on relatively low redshift clusters that would break some of these or fix some of these unknowns, like the turbulent dissipation scale or the injection scale?
Um, so oftentimes it's assumed when calculating the input energy that the injection scale is of order the size of the jets or the size of the bubbles. Whether that may be a reasonable assumption, and that's something you would directly measure from Axis. But really, it's certainly not well, it's just unclear. Okay. And so it's not obvious to me in the uncertainties that I just mentioned where Axis would contribute to that question, but I'd have to give it a little bit more thought. For example, cosmic ray heating, I'm looking more into the radio for that. And it's very hard to see a direct indication of that in the X-ray, for example. And then, in terms of the turbulent dissipation timescale, a lot of that, depends on subgrid physics and so on. And so that, there needs to be theoretical. I think it's a theoretical issue that needs to be addressed. But the direct stuff that we get from Axis will be just mapping outflows and measuring total powers and so on.
Okay, great. So we're going to switch over to our next speaker. So if you could just stop sharing. And then you want to share desktop. Let's see. Yeah. And then let's see if you click on yours and then view. It's under view. Yeah, I think. Screen. Okay, our next speaker is going to be Eileen Meyer on resolving X-ray jets and their impact with Axis.
Okay, so the next three talks are about jets. So I hope the three of us will be able to convince you that resolved X-ray jets are a fantastic science case for Axis, and only Axis can move us forward. We've done an amazing amount of discovery with Chandra, and Chandra really got us asking, I think, the right questions. But we need Axis for this science. So very rapidly through the intro here, we've got, of course, lots and lots of radio jets coming from a sizable fraction of AGNs out there. And as we just heard in the press talk, they're quite important in their impact. There's also a lot of things we don't know about jets still. So this talk is going to talk a little bit about some of the, our interest in jets themselves, but also how that's important sort of on the bigger picture. So despite, having radio catalogs now with, tens of thousands of resolved jets in them, going to higher frequencies is difficult. We have very limited numbers of optical observations with Hubble of these jets. Here's a really famous example, which is M87. But it really wasn't until Chandra was launched that we discovered that these jets not only emit lots of radio, but they are huge emitters of X-rays. So Chandra has now detected something like over 200 of these resolved jets on scales from hundreds of parsecs to kiloparsecs, hundreds of kiloparsecs, I should say. Lots of work and lots of people have done all this in the last 2 decades. And so there's still a lot of open questions that we're interested in terms of what's going on with jets. We're still not totally sure how they're launched in the first place, what they're made of, their particle content, how they're structured, what are these, how are particles being accelerated on these very large scales where we see the X-rays way outside the host galaxy. So I cannot focus on all the work we've done with Chandra over the last 2 decades, so I'll mostly focus a little bit on sort of I think the main question a lot of us have been working on, which is what is the origin of these X-rays? Because they were not expected at the level that Chandra saw them. Should say that there's a caveat. Chandra was not the first to detect X-ray emission. Rosat actually did detect this 3C273 jet, but I love showing these 2 pictures because it really highlights the revolution of going to the high resolution, because you can only really see this jet in detail with Chandra. And of course, this isn't even like the most beautiful image we've made. I think this was one of the first ones published. So something with arc-second scale resolution is vital for this science. And it's fun to talk about the very first target that Chandra ever observed, which was Park 0637, which was supposed to be a nice point source. And probably most of you know this story, that it turned out not to be, and they serendipitously detected the X-rays from that jet. And immediately, people were confused because it's actually rather hard to explain those. There's, right off the bat. So thermal Bremsstrahlung didn't make sense. Synchrotron self-Compton. ICCMB was an even worse model. This is from the original discovery paper. And so, of course, this was the origin of this idea that perhaps these jets remain highly relativistic on these, very large scales, kiloparsec scales, and they're able to upscatter CMB through inverse Compton. And so it's a little bit contrived. You have to kind of fit yourself into a weird parameter space sometimes in terms of how close the angle is to the line of sight. But you can make, your very sparse data, you can fit it with your model. And so this was very popular for a long time. And this is an important question because if it's not ICCMB, the only other real explanation for a high level of X-ray emission on these scales is that nature is producing multiple synchrotron emitting sort of particle populations, which is weird, and we didn't really expect that to happen. Spoiler alert, that is probably what's happening. But here's the sort of very, very rapid fire way that we showed that ICCMB is probably not happening, especially at lower redshifts. And so one of the big things was it predicted a lot of gamma ray emission. Fermi did not see this, and it should have. And then here's the list of everything else that has been done. Lots and lots of people have worked on this, including people in this room. So I won't read the whole list. I'm going to talk a little bit, though, about variability, because variability is really interesting, and it provides us with a lot of clues about what could be going on. But you'll notice that I think the best X-ray variability study, if I may say, which was done by my group, had to be done in a population context. We don't have the statistics beyond a few nearby sources to really study the variability of these jets in detail. We just don't have the photons. So many of you know about the famous case of Picture A, which was the first surprising result that these jets can fade, can change over just year timescales. Herman Marshall published that back in 2010. Martin Hardcastle's done a lot of work on the same source, Picture A, using the hotspot. And so this inspired my group to go and look at all of the X-ray jets that Chandra's observed more than once. And usually this was just 2 observations, usually a snapshot discovery and then a later deeper observation. So just 2, a handful have more. And so what we found was that we couldn't find any other cases where there was like a clear, 10 sigma, this is a variable jet type thing. But we kept finding these 2 and 3 sigma events, which was very provoking. And so I said, okay, we're not going to do these as individual things. We're just going to look at the population and see if there's a sort of a variability signal here. There's too much, it's too noisy, if you will. And so we worked with some statisticians at the University of Toronto, but we basically have a very simple model, which is that the null hypothesis is they're steady emitters, taking into account all the detector and observation characteristics. We would expect under our model that if jets are not actually varying, this is all just statistical noise. This distribution of p-values for all these individual jet not regions should be flat, should be uniform, and it wasn't. We kept finding this tail at low p-values, and that indicated that there was indeed too much variability. It was a little bit beyond what was expected. So this was fun. This was published in Nature Astronomy a couple of years ago. Just as a side note, if anybody's interested in a nice tool for testing if something is variable, which doesn't require you to have any particular sampling, it's just if you have at least 2 data points, you can use this maximum likelihood approach that's described in the paper. It's the script you need is this long. It's great. Yeah, so here's sort of the point getting towards axis. So how sensitive are the Chandra archival observations to variability? Because we weren't able to see a clear signal from individual sources, and even the population-based sort of evidence we have is broadly consistent with either sort of 30% of the sample being variable at a higher level, or maybe 100% of the sample being variable at a bit lower level. And so that's an annoying trade-off. And it turns out we did a lot of simulations to show we're only sensitive to variability if it was rising to this 10 to 30% level or more. Sorry, I said that backwards. We're only sensitive to if it's at 50 to 300%, okay, for most of our observation sets, whereas our evidence was that most variability is more like 10 to 30%. So really dramatic flares like we saw in HST1 of M87, not very typical. More likely what we're seeing is some lower level variability. I also have to take into account, of course, that we're probably averaging some emitting regions together. So we also did a few things looking at the sample. We had enough jets that we could at least divide the sample in 2, and we found that the variability signal was mostly coming from lower redshift core-dominated quasars. And so that means these high redshift sources maybe were steady, maybe were consistent with a steady model. And the reason we care about this is that the ICCMB, that original model that everybody jumped on for the X-ray emission, cannot have any kind of variability whatsoever, just absolutely not. So if you have something that's variable, it not only means you're back to a synchrotron explanation for your X-rays, but even with that, you have these, it's rather shockingly small volumes that you're now confined to. So you think that these X-rays have to be coming from some tiny, tiny region that's much smaller than the cross-section of the jet. So that seems important to know. Sorry, this is probably something I should have shown earlier. This is just our simulations again, showing you can kind of trade off between how big the variability is relative to sort of its baseline flux. So 10, 20% versus how much of the sample is variable, and there's this degeneracy. So as a sort of preview, I guess, of what we would see with much larger samples with AXIS, we have used Chandra to look repeatedly and very deeply. We're talking totals of 0.5 megasecond on M87 and others to see, and when we do that, these nearby bright jets that we've looked at over and over show variability. They always do. So Pictor-A, M87, 3C273, this is what's happening. And so I think it's likely that if we have a much more capable instrument, we're going to be able to study the variability of these jets in actual individual cases in detail and understand some more about where this is originating and what it means. This is just another case. So this is again 3C273. So you see all this beautiful data. So this is so much work, guys. This is you have to get radio, you have to get all this HST time, you have to get deep Chandra observations. But if you do get all that, you can actually do a resolved spectral energy distribution as you go from sort of tip to tail of the jet. And this is just beautiful data. But we have this for 2 sources, let's say. Okay, we can't do this with all the other jets we have. Here's a typical sort of case. This is this was by Schwartz et al. This is one of our 200 detected jets. Here's a typical, actually a good X-ray image. You see how many photons they have. And if you try to compare the X-ray and radio profiles, this is the X-ray counts, right? We're not doing any spectral analysis with 5 counts in a region. It's nothing you can do with this. So this is challenging because we see from 3C273 and sources like it that the X-ray spectrum is changing massively over the jet. And so that's going to tell us about the plasma deceleration and what's happening in the conditions. A lot of jets are just not detected in most of their extent. So we see the radio contours, and yes, we've detected the jet. We've got 5 photons associated with maybe one part of the jet, but the rest of it's not detected. We can't do anything with that, just have upper limits. So really important last point I'll make is that spectral analysis is important not just for understanding the jet, but also to make sure we're not confusing ourselves about what we're seeing. So, we do see jet-driven gas. So we see cases like 3C305, where actually the dominant source of X-rays here is shock-heated gas. It's well fit by an APEC model. There's a little bit of non-thermal emission coming from the hotspot. But if you take a source like this and you throw it up to really high redshift, and you're now with, let's say, Chandra detecting it with 5 photons, you're going to have a hard time disentangling what exactly is giving you these X-rays in a lot of cases. Okay, this is a point that it's really nice to be able to also connect this with things like O3 maps to trace outflows and understand, this impact of the jets on their environments. Okay, here's an example of some candidate X-ray jets at high redshift. For jets, most of them are below redshift 1, right? So we're just barely able to start seeing these high redshift jets, even though that's where things are really interesting. The CMB is much brighter, so we expect more X-ray emission, but we're just detecting them with handfuls of counts. And so also I should mention that most of these studies of high redshift jets were done fairly recently, when unfortunately Chandra lost a lot of its response. And so what we can do with AXIS is more than 10 times better than this, as it turns out, with the soft response coming back. I'm going to skip through these slides really quick and just go to the conclusion slide. So I think we've made a lot of progress in understanding X-ray jets. I mean, Chandra opened this to us as a thing that we need to understand. And I think we know now that probably the second synchrotron model is correct for lower redshift jets, but we still don't understand why nature does this. Why do we have multiple particle populations? And then what does it mean when we start to detect these high redshift jets? Are we seeing shock-heated gas? Are we seeing this inverse Compton signature coming up? What can we learn from resolve studies, going along jets? And so we need big population studies, which we just don't have right now. We have a lot of really great little studies of single sources, but these are super faint, and so AXIS will be great for them. So I'll leave it there.
So I'll ask you one question. So you get, a factor of maybe, 10 more counts. Which population would you study? Is it the lowest redshift ones, or is there a particular population you think is missing because we only have, a few prototypical examples?
Yeah, that's a good question. So we've got a lot more observations of the more powerful sources, obviously,
Right.
and that's always the tip of the iceberg. And your bulk of your population is going to be lower luminosity sources. So yeah, I think it would make sense. You'd probably want to do a little bit of both. So you'll want to do really wonderful deep studies of nearby lower luminosity sources that you can just do in exquisite detail, and then you'll have to pair that with the probably higher power sources at high redshift that you'll be able to detect easily. But I think the good thing is that with AXIS, you're no longer, we've had the hardest time getting complete samples, because people don't like fishing expeditions where you don't know if you're going to detect anything and your upper limits may not be that interesting. And so with AXIS, it's we'll pretty much guarantee you that we will get X-ray photons, because there's a point where that ICCMB emission has to be there. It's mandatory. So we'll, I think, be able to always detect the X-ray emission from these jets with AXIS, which is nice. Make it easier to make your sample.
Okay, Richard? Let me give you that.
So, just a little question. Have you estimated the exposure times that AXIS would need to get the science you want?
I've done it for a couple cases. This is M87. So you get basically comparable results in 5 kiloseconds.
Okay.
Compared to 300 kiloseconds.
So is that because that's including the contamination effect on Chandra?
Yes. Yeah.
Okay.
So this is, you need more Chandra time because of that. So
All right.
yeah.
Okay, well, that's an enormous effect. But and so that was the next question. Is it primarily the soft response of AXIS that's giving you the extra signal, or is it the total band?
Both, probably in about I should actually check if it's equal measure. I'm not sure. Probably the larger effective area is the most important, but that soft response is important, especially for things like distinguishing between non-thermal and shock heated gas. Without the soft response, that's harder.
And the slight degradation in spatial resolution is not a killer.
Say that again.
The difference in
Oh,
spatial resolution.
Actually, if I'd had more time, I would have gone on a whole thing about knowing your PSF and how important it is. Because you can overcome a slightly, broader PSF if you have more photons. You can do the modeling. We've done amazing things with Delico and Lyra with jets and doing all these deconvolutions, and it's really fantastic. So I think we'd be able to do similar things with Axis.
Okay, so maybe just one last question.
Okay. Oops, sorry. Thank you very much. I have just one naive question. So you said the ICCMB model is more dominant likelihood in the high G region, and that's because in the high G redshift we are not seeing any variability in X-ray. But also you had a whole list of the explanation why ICCMB has it like challenges. So what about those?
And that's because our sample is super dominated by low redshift sources. So we've almost entirely looked at redshift below redshift 1. And if you look at, this is a very nice plot from Neil Brown's group. I always forget to put it's on there, sorry, Zoodle. This is where they show this X-ray enhancement that's showing up. So this is not resolved studies, this is just total X-rays, but they see extra X-rays coming from jets at redshift like 4 and 5. And that is actually due to the jets being, the extended jets, Kiloparsec-Scale jets being so strong now that when you take the total X-rays, you see this enhancement, but it's not coming in until those redshifts. So it's like out to redshift maybe 3, you don't even expect it to dominate. So yeah, we need the high redshift samples to be studied in detail, which we just can't get the counts with Chandra, even if we stole it for all of its time. So thanks so much.
Okay, great. So let's switch speakers. Okay, so our next speaker is going to be Eric Perlman talking about observations of the extragalactic jets with Axis.
All right, so first of all, it's great to be here and to be talking to you about what Axis can do for jets. And so I'm going to approach this a little bit differently from Eileen. And the reason that I want to do that is because I really want to concentrate on what it is that you can do with deep observations of jets. And I'm also going to concentrate a little bit more on a multi-wavelength approach because that has been kind of the hallmark of the way that I've approached them. And I think that jets, since we see them in so many different wave bands, all the way from the low frequency radio all the way up through the gamma rays, we need to do that. Okay, so just to remind you, jets are a Chandra legacy. Oh, wait a minute. There we go. I skipped this slide. They're a Chandra legacy. We found out about X-ray jets a little bit before Chandra, as Eileen mentioned, because ROSAT did see the X-ray jets of 3C273, M87, and Centaurus A, but the fact that there were a lot of these objects was really one of the first discoveries of Chandra, and it's a Chandra legacy. This is, of course, Parks 0637, and this was what first put us on to the fact that these were common. This was supposed to be a point source. Obviously, it wasn't. So what do we know about these objects? Well, as Eileen mentioned, the X-ray emission can arise from a couple of different possibilities. It can arise from either high energy synchrotron rate emission or inverse Comptonization of the CMB. And if it's inverse Comptonization of the CMB, they have to be beamed and seen at small angles. So here's a little bit of a quandary. How do you tell the difference between the two? And can you tell the difference between the two in a spatially resolved way? And that's actually important because it may be that in some jets, you have one emission mechanism working in some of the knots, and in another few knots, you have the other emission mechanism working. You need spatial resolution to do this. Well, if you want to tell the difference, you need some things. You want deep imaging and X-ray spectra and SED of all of the knots. This is where the problem is. Oh, and you need some multi-wavelength information. And the reason you need multi-wavelength information is because you want to take a look at the properties of that second emission component, whatever it is, and you want to tell definitively whether it's synchrotron radiation. Well, if it's synchrotron radiation, then it should be polarized. Well, we can't do arc-second resolution X-ray polarization yet, but we can do it in the optical if the X-ray emission connects to the optical. And so, whoa, what happened here? This is what I wanted to show. So these are results from my grad student, now finished, Devin Clautice's work on 3C273. And this is HST observations of the 3C273 jet. For those of you that do not remember, the jet is all the way off the field to the left. And on the top, you see Stokes' eye, so total intensity. And on the bottom, you see polarized intensity. And what is extremely obvious is that there are a number of parts of the jet that are very highly polarized in the optical. And this component, as you will see later, is connected to the X-rays, okay? Now, for jets like 3C273 and Parkstow 637, the issue of whether we could see polarization was important because we didn't know whether that high energy component was synchrotron radiation or whether it was inverse Comptonized CMB radiation. Inverse Comptonized CMB isn't polarized. And the reason it isn't polarized is because the seed photons are not polarized. Okay? The seed photons are the CMB. They aren't polarized. So, here we have very strong evidence that it is synchrotron, and it's because we see high polarizations. And just for reference, we're talking about polarizations between 10 and 40% in the jet of 3C273. Now, as Eileen and her group, and I've been in on this too, have done, another way you can tell the difference is by looking at the extreme high energy tail of that second emission component and look for whether it is emitting GeV gamma rays. And so the GeV gamma rays are a second way you can tell the difference. The two results basically agree. Now, all of this works great in concert with future observatories. So in particular, JVLA, JWST, HST, well, HST no longer future, of course. So let's go on a nice little tour of the jets that we really can see well and that we have nice images and spectroscopy. So I'm going to start with M87, which is an object that I've worked a lot on. And at the top left, you can see the Chandra data, this is all 140 some Chandra ACES observations co-added together. And you have two different views on the left. The top view is smooth. The top view is zoomed in on the center, and so you can see the jet and also the inner parts of the high energy extended emission. You can also see point sources from the galaxy, and the bottom view is a much wider view. M87 is great because it's only 17 megaparsecs distant. We see X-rays from every knot. There is X-ray superluminal motion, and there is variability. Just to remind you, here's your superluminal motion in the X-rays. And it's only been seen in 2 regions, but it tracks with what's seen at with HST. So that's really nice. And of course, here is the variability of HST1. And I particularly like not just the flare, which this all comes from Dan Harris's work, but if you focus in on the figure to the right, that is the cumulative effect of 20 years worth of Chandra observations. It's from Sun's paper. And you can see that HST1 didn't just have that flare. It was varying for a very long time and in a really dramatic way. Now, on the right, the 2 images show the X-ray spectral index as a function of distance along the jet. And that is in this bottom panel here. And what I want to point out is that even with close to 2 megaseconds of observations, which is what we have on M87, it's still not great. All right. This is what you can do with Chandra spectra and imaging. What you're looking at are, on the left, the spectral energy distributions of each of the knots, and then on the right is synchrotron models of the jet. And this gives you the particle energy distributions in each of the knots. And you can see that they are tremendously varied. And it's actually not true that FR1 jets are all a single population. They're not. Okay, you can see that 3 of the knots require 2 electron populations. And in fact, all of the knots, turned out, require that the fraction of the jet that emits in X-rays is less than in optical, and it decreases with X-ray energy. Okay, Sen-A. Sen-A is much more nearby. Of course, it's only 4 megaparsecs. It's 100 times less powerful. It's not as indicative of other jets, but it has a really nice complex structure that you can see with enormous physical resolution. The Chandra data, close to a megasecond, and you can see that the X-ray spectral are not that great. The X-ray spectral indexes are not that great. Let me cut to 3C273, and because I want to spend some more time on 3C273. So 3C273, you're looking at the Chandra image on the top, HST on the bottom, and then the radio is the third panel. They're enormously different. This is one of the things that is really underappreciated, is that Chandra sees a different jet than in the optical, than in the X-rays. You have an enormous diversity in the spectral energy distributions. And you can see what the Chandra bow tie looks like. This is from 200 kiloseconds of data. So even in the bright objects, you need a couple hundred kiloseconds to see the X-ray spectrum. By the way, this bit about different X-ray morphologies, it's common. So this is 3C111, and this is work again by Devon, and you can see that there are differences not only between X-ray and radio, but also X-ray and optical. All right, back to 3C273. So this is a zoom up on the jet, and now I'm showing the polarization data and its full power. And what you see is that there's a tremendous amount of diversity. So the message here is that we really need access because we want to do this for more jets, but we really need other observations to other wave bands. All right, so what is missing? Jet science is really at the hairy edge of what Chandra can do. I showed you some really nice results, but they came from only 4 or 5 objects. Chandra images of other jets just aren't good enough. So I just picked 3 at random, and these are 3 relatively good cases. And you can see that, yeah, we detect the jet. We see that there are knots, but it's not that good. We typically only have of order 5, maybe 10, maybe 20 counts in a knot. We don't see emission between the knots. We can't do any spectral analysis with this. There is work underway on deep imaging of a few jets, and I'm going to show you one of them in just a second, specifically Parks 0637. That is by my team. All of them, the goal was to get about 100 counts per knot so that we could get limits on the X-ray spectral index of about 0.3, 0.4. Well, we got that, but it's not that great still. And in fact, here is some of that data. Here is the Parks 0637 jet. And you can see that now we really do resolve well those knots. And there's optical polarization of 3 different knots in the jet. The vectors that you see there are the HST polarimetry. And yeah, so Parks 0637 is also synchrotron. But interestingly enough, we don't see optical polarization everywhere. We only see it at the leading edges of the knots. That's really interesting. Chandra images of other jets just aren't good enough. So what can Axis do? And this is my final slide. This is what we want. And this is what I put in our science case. We want a sample of like 20 to 40 X-ray jets. We want to split it up between multiple different classes to really get a survey of the entire population. The typical exposure time is about 25 kiloseconds. Lots of this can be done in conjunction with other observations because lots of these targets also have, for example, galaxies and clusters. And there are many other reasons why Axis might want to look at them. You get really nice morphology on the jet. We don't know what we're going to find. So I actually did not do simulations of individual sources because I didn't feel it was the right thing to do. And of course, we get spectra, and who knows what we're going to find. Thank you.
Okay, so we have time for a few questions.
So, of course, targeted observations are going to be crucial for this, but I'm wondering what fraction of sources are already in the planned survey fields where you're going to get enough data to take advantage of this completely for free?
So that's an interesting question. I don't know the answer to that. I actually wonder if Chris or Aaron can help me with that.
Your famous sources are not going to be in our survey fields, because of course our survey fields are trying to get deep extragalactic, typical volumes. The last thing we need is a big cluster in there with a powerful radio source. So by default, no, we won't be catching any of the famous jets in these sources. But that did lead me to my immediate question, which is actually for both you and Eileen. As we go to high redshift and you've got the 1+c to the 4th effect. How many ghosts are we going to find? Radio galaxy ghosts.
Right.
I mean, I know Chandra's seen a small number, but is that something that's going to start popping up and becoming quite a large?
So X-ray emission from high redshift jets.
From high redshift jets or high redshift cocoons that are left over from jets turning off?
So I would say there's going to be a significant number, and the reason why is because, as Eileen mentioned in her talk, ICCMB is a mandatory thing. You can't get away from it. And at high Z, 1+z to the 4th is going to help us quite a lot. And so Z of 5 source, 1+z to the 4th, that's 6 to the 4th, right? So that is a huge brightening in the CMB and hence the ICCMB. Now, there is a problem. The problem is that ICCMB, at least at low redshift, requires the jet to be beamed, and it requires a small viewing angle. Add to that the fact that, of course, the resolution needs to be high. Now, the problem is that if ICCMB is energetically important, you have what's called the Compton rocket effect. What that means is that ICCMB becomes an effective cooling mechanism, and it also slows down the jet because there is a recoil from the Compton process that robs the particles of their momentum. That's a problem. That means the jet slows down. That means you have short jets, and that resolution is going to be an issue. Eileen, do you want to comment?
Well, say for relativity, it'll be more extended. So I think that'll actually probably worth a simulation to see. Especially with the higher background.
Let's work together with it on that.
But yeah, you should see it pop up in the recording.
I have a comment and a question. My comment is, Chris, your question harks back to a fascinating but totally incorrect paper by Fred Hoyle in 1965, who tried to connect Giacconi's new X-ray background with Penzias and Wilson's brand new cosmic microwave background, and said that that produced was entirely due to inverse Compton of radio lobes. Incredibly incorrect by orders of magnitude, and yet Axis may see it. My question to you, this is to Eric and to Eileen and to Onik after lunch. There was a decades-long debate as to what is the positive particle in jets coming out of black holes. Is it positron, electron, or is it proton, electron? The factor of 1800 completely affects the issues of energetics. I believe that, if I understand a little bit, it's sort of tending towards positron, but I don't know that, and I wonder if you think that either this is known from Chandra or whether Axis will help understand that question.
Do you want to take this, or do you want me to?
I see the Hardcastle group is coming down firmly on like FR1 types or training that there's fairly large head.
I'm sorry.
Yeah, let's.
Oh, sorry. Sorry.
Is
loud.
it positron or proton?
It depends on the jet.
Yeah, let me comment.
Where,
further.
yes, where is important.
Yeah,
Yeah.
let me comment further on that because, so this is something that Marcos and I did a fair amount of work on with Park 0637, and it's really tough because what we were hoping to find was bulk Comptonization from those positive charge carrier, and in particular from the quiescent part of the jet. This is something you could do in 3C273 as well, basically to see either X-ray or optical emission where there was, not very much. We didn't find any. As Eileen said, the evidence seems to be pointing towards a light jet, which means the positive charge carrier is positrons. Now that means a much less powerful jet from the kinematic standpoint. The question is what we see at high redshift.
When the cosmologists, computational cosmologists, calculate AGN feedback, do they assume a heavy jet or a light jet?
I'm actually not sure.
It must matter.
I actually am not sure myself.
I don't believe they are doing the physics at the level where it matters.
Okay, well, maybe there's something for Access to do here.
Is
I
it
think
possible to
there's a lot of
comment?
tracks.